Another colligative property that we mentioned already is freezing point depression. Boiling point elevation is another one. When we look at a phase diagram for a substance, so let's make sense of what we've got going on here. Here we have, in blue, we have the pure solvent. So if we look at 1 atmosphere and we go across increasing temperature, we come to the melting point and it converts to a liquid. And if we keep heating the liquid, increasing the temperature, eventually it will begin to boil. Remember that boiling happens when the substance's vapor pressure is equal to the atmospheric pressure above it. We just saw that adding a solute, here in red, the solution, causes the vapor pressure of the solvent to be lowered, right? It lowers the vapor pressure. So this whole curve is lower. What that means is, as we go across, we have to heat it higher to get it to boil. So the boiling point is elevated. The boiling point gets higher. The melting point gets lower, or the freezing point. So freezing point depression, boiling point elevation. Freezing point depression always makes me think of living in the Midwest, where people get depressed in the winter because it's really, really cold, and we all have seasonal affective disorder, and there's so little light that everybody's just like, ugh. So it's freezing point depression, but that's not what we're talking about here. Lowering the vapor pressure means that the solution has a lower melting point and a higher boiling point. I used to have a hard time remembering which direction these things went. And so what I finally came up with is that it takes, what adding a solute does is it means that this solution will stay a liquid over a wider range. So the melting point moves this way and the boiling point moves that way. And so you have a larger temperature range over which it will stay a liquid. That's how I remember it. We can, of course, measure the freezing point depression and predict what's going to happen. And this is the equation. The change in the freezing point is the molality of the solution times a constant. And that constant is going to vary and be specific for a solvent. Again, what solute you put in there doesn't matter, it's the number of particles. And that's why we have to look at the molality, because that's the moles of solute per kilogram solvent. Molality is used here because it doesn't change with temperature. When we're doing temperature stuff like this, the temperature is changing, and like we mentioned last week, molarity changes a little bit with temperature because the volume of the solution will change. The mass of the solution does not. So here's a table from your textbook showing some freezing point depression constants. So here's Kf, and the unit on that is usually degrees Celsius per molal. And that reminds you, oh, I multiply this by the molality, I get the freezing point depression. It's the freezing point depression, and so you have to consider what the normal freezing point is, and then you would subtract the freezing point depression to get the new freezing point. So, benzene, carbon tetrachloride, chloroform, all of these guys. Also in this table are the normal boiling point and the boiling point elevation constant, and we'll talk about that in just a minute. So let's calculate the freezing point of a 2.6 molal aqueous sucrose solution. We need the freezing point depression and the normal freezing point for the solvent. This is an aqueous solution. The solvent is water. I'm going to go back to this table. Here's water. The normal freezing point is 0, and Kf is 1.86. So Kf is 1.86, and that was degrees Celsius per molal. So our freezing point depression, delta TF, the change in the freezing point, equals the molality of the solution times KF. So the molality is given to us, 2.6 molal times 1.86 degrees Celsius per molal. 2.6 times 1.86. So delta TF equals 4.836 degrees Celsius. Is that the freezing point? No. The normal freezing point is 0. Delta TF being 4.8 means the freezing point is lowered 4.836. So the freezing point will equal the normal freezing point minus this change. So the freezing point of the solution will be minus 4.8 degrees Celsius. Any questions? Boiling point elevation, very similar equation. All you do is change the F's to B's. The change in the boiling point is the molality of the solution times the boiling point elevation constant. So antifreeze in your radiator serves two purposes, and it's due to the colligative properties. It causes the boiling point of water to go up, which is important in warm situations, like around here in the summer. You don't want the water in your radiator boiling. The pressure goes way up and something blows. So by adding antifreeze, the boiling point goes up and it can cool your engine at higher temperatures. You also don't want it to freeze. We don't have to worry about that here, but in Minnesota, where I grew up, it's a big problem. If your radiator freezes, the density of water is greater than liquid water, and just like a water bottle in the freezer, it will break your radiator. So by adding ethylene glycol generally to the radiator, we lower the freezing point. We can, of course, calculate this, calculate the boiling point of a 3.6 molal aqueous sucrose solution. Well, we need Kb for water, so we have to go back over here, and we also need to know what the normal boiling point is, 100. Kb is 0.512. So the boiling point elevation constant for water is 0.512 degrees Celsius per molal. And constants like these are something that will be given to you on an exam. You don't need to memorize those. So the change in the boiling point equals the molality of the solution times the boiling point elevation constant. These questions are simple because they actually give it to us in molality. Sometimes they might give it to you in something else, and then you have to actually calculate the molality. So 3.6 molal times the 0.512. It always amazes me how I can say one thing and write another. That time it came out, the writing was correct. 3.6 times 0.512. So the boiling point elevation is 1.8432. This time this has 3 sig figs. That's degrees Celsius. That's the change in the boiling point. It's not the new boiling point. That would not be a boiling point elevation, would it? So the new boiling point will be the normal boiling point plus the change. This is actually an exact, you can consider that to be an exact number, because the Celsius scale was really based on the boiling point of water at atmospheric pressure. So then our boiling point is going to be 101.84 degrees Celsius. Any questions? Another colligative property is osmotic pressure. Osmosis is the flow of solvent from a solution with lower concentration. It's backwards. No, it isn't. Never mind. Brain fart. The solvent flows from low solute concentration to one of higher solute concentration. And this is a process by which seawater causes dehydration if you drink it. It has to do with entropy and the mixing of solutions, the dispersal of energy. A semi-permeable membrane, if you're not familiar with it, semi-permeable, it's partially permeable. It allows some things to pass and not others. Biological cells contain lots of different semi-permeable membranes. Generally, it'll allow the small particles to pass and not the larger ones. So water will go through, but solutes will not. We can set up an osmosis cell. When I was in college, we called these U-tubes because they're shaped like a U, and now YouTube has a completely different meaning. It's a website. But this U-shaped tube, dang it, I changed the color. Oh, well. Put a semi-permeable membrane in the bottom here, separating the two different sides. We have pure water on one side, and we have a solution on the other side. Maybe this has sodium chloride in it. And then we wait. And what happens is the water will move from the less concentrated side to the more concentrated side. In Mrs. K's chemistry land, you think of it as trying to dilute that. You've got more. We have to dilute you. We have to all be the same. Nature's a lot about trying to get everything the same. The water molecules will move to the other side, diluting this solution. Why don't the solute particles move from this side to that side? Well, they would if they could, but the semi-permeable membrane won't let them do that. So the water's the only thing that can move. So the water will move, and that will cause the volume on this side to be higher, and the level of the liquid will rise. It's defying gravity, isn't it? Well, when you have a U-shaped tube with different levels of liquid on each side, you have a difference in pressure. This will rise until this difference in pressure is equal to the osmotic pressure of the solution. And that has to do with how the concentration, the number of moles of particles per amount of solution. So depending on the concentration of this solution, that is what will determine how high this goes. Any questions? It was a rather jumbled up explanation. Of course, we have an equation for this as well. That's a capital pi. Looking forward to pi on Thanksgiving. Osmotic pressure is the pressure needed to stop osmotic flow. So if we go back to this, how could we get these water levels to be equal again? We could put pressure on this side. The amount of pressure we would have to apply to force the water back to the other side would be equal to the osmotic pressure. You've heard of reverse osmosis, water purification systems. That's the principle on which they work. You apply a pressure to cause osmosis to go in the other direction, and you get pure water from contaminated water. So the osmotic pressure is equal to the molarity of the solution times the temperature in kelvins and the gas constant. That's the ideal gas constant, our old friend, 0.08206 liter atmospheres per mole Kelvin. So calculate the osmotic pressure in atmospheres of a solution containing 1.5 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. Well, osmotic pressure. So osmotic pressure, pi, is the molarity times the ideal gas constant times the temperature. Pi equals Mr. T. I just saw that. I bet Mr. T likes pi, don't you think? He looks like someone who would like pi. Pi equals Mr. T. So M is the molarity. We need to find the molarity. R is the ideal gas constant. So we don't need to look that up. We know that. And T is the temperature in Kelvin. Let's start with the molarity. The molarity, we need moles of ethylene glycol, I'm going to call him EG again, per liter of solution. So we have 1.50 grams of ethylene glycol, and we need to convert to moles. 2 times 12.01 plus 6 times 1.008 plus 2 times 16, 62.068 grams per mole. .5 divided by 62.068. So this is 0.024167 moles. And we've got 50 milliliters. So I'm going to put the moles up here. 0.024167 moles. I'm going to throw caution to the wind and convert milliliters to liters in my head. 0.0500 liters. Those 2 zeros are both significant digits. We can't just throw them away. They need to be in here. So we take our moles, we divide by 0.05. This is still going to have 3 significant figures. I get a molarity of 0.483. Throw in 2 extra digits. That's moles per liter. So pi equals Mr. T. 0.48334 moles per liter. And then the ideal gas constant, that 0 doesn't want to be made. There we go. 0.082006 liter atmospheres per mole Kelvin. Oh, we've got the moles and the liters canceling out already. And then 25 degrees Celsius plus 273.15 is 298.15. That's not a 5. That's a K. I need that. And the kelvins cancel out. 0.48334 times 0.08206 times 298.15. No room for the answer. I'm going to get 3 sig figs, 11.8 atmospheres. That seems pretty high. That's what it came out to, though, isn't it? I didn't push a button wrong. Okay. So you put 1.5 grams of ethylene glycol in 50 milliliters of water, and in order to keep osmosis from happening, you're going to have to apply 11.8 atmospheres of pressure. Any questions?